Hello students, welcome back. The final topic here is direction fields. Not everybody completed Calculus 3, multivariable calculus, so not everybody is familiar with the concept of vector field, so I'll have to review a little bit further along the way. A vector field is a map that sends each point to a vector. And in calculus level, vectors can start anywhere, and it is convenient to drag all those down and make it into position vector starting from the origin. But in higher level, we usually consider vector field with vectors starting at the point. So given point, we assign it to a vector starting at this point x, y. Okay? And a direction vector field of first order differential equation is x prime y prime, so the direction of the derivative, so direction of the x and y's movement, okay, the motion, the derivative comma derivative, that is the direction of the motion, and assign it to the point. So that is direction vector field of an ordinary differential equation. We have a lot of notations here, but it's going to be hard to understand. So let's go over to example. So here's an example. So y prime is y. So given xy, given xy, we are assigning that xy into x prime, y prime, starting at this x comma y and this vector. Okay, but in this case, x is just t. X is t, time. So x prime is actually 1. You see, x and t are the same. This is this coordinate is ty plane because x and t are the same in this case. So this is 1. So this is just 1. And the y prime is, what is y prime? Y prime is equal to y, isn't it? So that's the vector. So at each point here, for example, look at my mouse. Horizontally, I'm moving by 1, that direction. So horizontal speed is 1. Vertically, I'm moving by y. So at this point, I have appropriate y coordinate values. So horizontally by 1, vertically a little bit, about 5 or so. So we have this arrow. Now, if you go farther up, then I have bigger y value. And therefore, we have longer arrow and going up further. Now, if you come down here, horizontally 1, so horizontally the same, and vertically relatively little because y value is small. Do you see those? So if you follow all those arrows in the same y coordinate values, they're the same. Y values are the same, and then horizontally they're all 1. So we have these kind of vectors starting at given points x comma y. So those are direction field. And how does the direction field help? They tell you the direction of the solution and which way the solution is moving. Now, in order to understand why it is related to the solution, then you have to go down to the previous lesson, the optional lesson about information flow. So you have to follow the flow, but that was a little bit difficult to walk, so not everybody probably followed that. So I'll take a jump and then ask you to follow the arrow, and that's about it. So if you follow the arrow, you're going to get the solution curve. And this is a solution curve that we discussed earlier. We have a bunch of general solutions here. And then for this particular initial value, we have this curve and then red curve. Now let's put those two together. Direction field, those arrows, and then gray are the general solutions. And do you see all the solutions are actually following the arrows? This gray curve following the arrow, that gray curve that's following the arrow, all the general solutions are following the arrows actually. So given any condition anywhere, we're simply following the arrow, and then that'll give you the solution basically. And why we should follow those, then it is related to the information flow. If you didn't follow, if you didn't quite understand that part, then just skip that. So follow the arrow through this initial value, then we have this blue curve, and then follow the arrows through this initial value, red point, then we get this red curve and so on. That's what the direction fields does. And why is it so useful? In case if you do not have algebraic expression of the solution, and sometimes your equation itself is so complicated, it came from experiment or something, in that case, you have to use numerical method. And numerical methods, there are many numerical methods, but one of the easier way to follow is to plot this direction field, again numerically, and then following the arrow, you can get approximate solution like that. How about the next example? Again, let me go to the direction field. Goes like this. Let's see. So point x comma y, we assign that to x prime, y prime, starting at the point x comma y, and that's a vector. But then again, what is this vector? Again, x and y, x and t are the same. So x prime is just 1. And what is y prime here? Y prime is equals to negative 2t y squared, isn't it? What's y prime? Y prime is equal to negative 2t y squared. Do you see it? So that's the arrow, that's the vector. So horizontally, horizontal speed is just 1 all the way. Now vertically, let's see, negative 2ty squared, and let's see, x and y the same. So let's use x there. So negative 2x. So for example, if I select this point somewhere here, around here, then let's see. Y squared is always positive, and then negative 2x. So when x is negative, x is positive, excuse me, in first quadrant. So negative 2x, so we have negative. Y squared is always positive, so overall negatives. So as you can see, arrow is pointing downward, coming down. about the point here over here in fourth quadrant? Y squared is always positive, negative 2x. X is positive here to the right hand side, so arrow is coming down. How about points over here? Arrow is going up because x is negative, and so on and so forth. So if you follow arrow, you're going to get solution curve, and we saw it before, that's the solution curve. And then let's graph them together. So gray curves are general solutions, part of the general solutions, and all the gray curves are actually following the arrows. And toward the corner, arrows are really long. So because these arrows are so long, around here, relatively speaking, arrows are very short. So I see a kind of triangular pattern. It just shows you the direction, but the magnitude is kind of impossible to tell. How about the x-axis here? Looks like we're having some separation here at the x-axis. What happens at x equal to 0? Or t equal to 0? X is equal to, so that's 0. So this entire thing is 0. No, excuse me, at the x-axis down here. So y is equal to 0. Sorry about that. Y is equal to 0. Y is equal to 0. That's 0. So this whole thing is 0. And what do you have? Y prime is equal to 0. Speed is 0. So if you fall anywhere on the x-axis here, horizontal axis here, then you're not moving. The speed is 0. So all the points in this horizontal axis, t-axis or x-axis, whatever you may want to call, x and t are the same, and you're not moving at all. So along the equator, no wind. So that's an example of direction field. Let's see, do we have enough time to show another picture? Okay, let's see another picture here. All right, we have the differential equation here, another differential equation there, and then we have two different initial conditions. And there's a bit of a surprise to this one. Did everybody do this problem? Well, here's the general solution, and then plug in the initial condition and then solve it. And you're going to get one solution. And then there is a trivial solution too, as a matter of fact. You're going to recall that if you have done this problem. Plug in t equal to 0 and y equal to 0 and solve for c, and c equal to 0, we have one solution. But there's another solution. Y can be constantly 0. Y is constantly 0. If this is constantly 0, then dy dx is constantly 0. Everything stays at 0, no movement. So there's another solution called singular solution, and here's a visualization as a matter of fact. You see, we have square root of y here, so y has to be always non-negative. So less than 0 doesn't make any sense. So we have arrows only up here. And then let's see, what kind of direction field do we have? X comma y is assigned to which vector? X prime comma y prime positioned at x comma y. And what is this vector? What is this vector? Okay, x prime, this time x prime and x and t can be different, so let's keep it at x prime. Okay. And then let's see, what is y prime here? X times square root of y. So this is x times square root of y. So that's the vector we have. If I take x is equal to t to make it simpler, then, well, okay, make it simple. And horizontal movement horizontal direction, horizontal speed is always 1, okay. And I made it simpler like that. And then x square root of y, what does that mean? Let's see, if x value is larger, we have bigger values. So compared with the arrows here, these arrows here are shorter. And also square root of y, as we move up, longer arrow, come down, smaller arrow. What if y is equal to 0? Down here, this whole thing is 0, so no motion along the x-axis down here. So if this is 0, then the whole thing is 0, so no motion along the x-axis. In the end, we have some U-shaped, going down, 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 up, up, up. That's the direction field. And then we are following a bunch of general solutions here, solution curves here. And among them, this blue curve is the solution coming from the initial value problem. But how about this green, the singular solution? Y is constantly 0. Y is constantly 0, then that part is 0, the derivative is 0, everything makes sense. It's just a singular solution that we usually wish to avoid, but in this particular case, we cannot avoid it. So we have two solutions. One is the real solution that we want, and another is singular solution. Or we could have the singular solution and suddenly it's taking off blue, or vice versa. It came down and then changed to singular solution, stay at green. We can have various different scenarios as a matter of fact. But still, you can see all the solution curves. In general solution, these gray curves are following the arrows, right? How about the next solution? Do we have enough time? Okay, all right. Here's a visualization. Same arrows. And then we have correct solution red. And then we end up with bogus solution down here with drawn in an dotted curve, which is going transversely with the general solutions and then the arrows. So this green part is not really a solution, it's a bogus solution. And if you actually have done this problem, you would understand this, where this bogus solution is coming into play, or extraneous solution. It is related to taking a square and square roots, so we have that artifact, plus minus artifacts there. But this extraneous solution is extraneous between negative and positive too, but outside that's valid. So the solid green is actually following the arrows there. As far as the initial condition is concerned, however, this red is the only one. And as for the direction field, it's the same as before. So I'll just copy and paste this thing down here. Yeah, that's the direction field, same as before. And then I'll leave it at that. As for the further analysis of these solutions, they're all here. Let's see. In this example, I think, yes, all here in this example. And I want to sweat out on yourself. I'm not going to do this for you. It's a fascinating example. Yes, a bit difficult here, but it's a fascinating example. I don't want to spoil the fun. I showed you a bit of a preview and extraneity. I want you to work it out. This one is actually much easier, but I'm going to leave that to you as well. So much for direction fields. Thank you.